Yay.
Welcome to Fiber Optics Lecture 2. Last time, what did we do? Remember?
Talk about angles, Snell's law.
We talked about the fact that we can predict, based on the relative densities of two different materials, that what will happen when a ray of light impacts that material. And we said that based on what we understand, one of two things is going to happen, right? What were those two things? What two things? Somebody mentioned it before we started. What two things can happen to that light ray?
Reflection or refraction?
It can either reflect or it can refract. How do we make the decision as to whether it reflects or refracts? The angle of approach tells us whether it will reflect or refract. Okay, so, and you've probably seen this, if you drop a rock in the water, it just sinks, but if you skip it along the water at a certain angle, it bounces, right? So there's gotta be an angle where it's kind of, has to make a decision, right? There's one angle, there's one particular angle where if you exceed that angle in one direction, it will reflect, and if you exceed that angle in the other direction, it will refract. But there's one angle in the middle that we're going to call the critical angle. Squeaky. And if we hit with the angle that's the critical angle, then what will happen is the light ray will propagate along the boundary. Okay, if it's less than the critical angle, what happens? It reflects. If it's greater than the critical angle, it refracts. Okay, and that's the game that we ultimately want to play, is this critical angle game, so that when we are trying to bend light as it goes in from a non-directional light source, if we're trying to bend light, ultimately what we want to happen is we don't want this. We want something that happens like this, where the light gets steered by different values of density, and it gets steered somewhere along the line, reaches that critical angle, and then goes along that boundary. Remember, looking at the end, this is like a ring, like a tree. And as light goes in, if it's coming in from the side, it's going to come in like this, and at some point it's going to hit a boundary right at the critical angle and go directly through the tube. Okay, so to get slowly steered by hitting denser and denser material, and that forces it then to take a path of least resistance at some point. Kind of like when you go walk along a fence. You know, you're going to walk along a fence at some point. If the fence is only this tall, you can step right over it. But if the fence is this tall, it makes it a little bit more difficult. And at that point, you've got to follow along that fence, and you've reached at that point somewhat of a critical angle analogy. Okay, so when we have all of these bands of different densities, they represent little fences of increasing height, and eventually the light will find its way down through the critical angle, down straight through the other end. Okay, and again, the goal of doing that is so that when we send a waveform that looks like this, we don't get a waveform that looks like this. Okay, with early, straight stuff, and then late stuff that bounce. Otherwise, we lose the integrity of our energy, of our bit. If this is 0, 1, 0, this becomes just slop, right? The longer the distance, the more slop it becomes. So here it might look like this. And that's why you have limits on how long cables and things like that can be. Okay, and we're not going to go into any more of that horrible, horrible math today. It's Thursday. Math is for Mondays. Somehow I've managed to swap out 2 of my markers. Okay, so are we all clear on this idea that when we have a boundary of 2 different materials, at some point light can be forced to travel along the boundary? Agree? Anybody have a question on that? And that is what you are striving for when you are standing over here skipping a stone. You're aiming for that critical angle so that it goes as far as it can in that direction, and the majority of its energy is directed in the direction that you want it to travel, right? All right. Anything look familiar about that? What is Roy G. Biv? It's the color spectrum, colors of the rainbow, right? How many of them are there?
7.
Why are there 7? Somebody do me a favor. Look up the word indigo in your phone. Look up the word indigo. Anybody got an answer? How come it's taken so long?
Let's see.
Besides the color, or?
We gotta sort through all the urgent care and get to the color.
Color of the rainbow?
Number of hues in the region of blue.
So do you have a picture of what it looks like? You have a picture of a color indigo?
50 Shades of Indigo. There's a bunch of colors.
What is it?
A bluish purple.
It's like blue and purple.
It's blue. It's dark blue.
That isn't what this is showing. It's showing purplish.
Well, indigo is a dark bluish color.
Violet,
Yeah.
It's almost the same as violet, and it's almost the same as blue. So, in a sense, it really doesn't need to be there. It's kind of an intergrade. But it's interesting that at the time, they came up with 6. This one wasn't there at the beginning. That got added later. I think that's the one that got it added later. because 6 was an evil number and 7 was a lucky number. So we wanted to make sure that we had 7 colors in the rainbow. Little bit weird, but hey, we're stuck with what we're stuck with.
1675.
All right, it's kind of like that cloud 9 thing. You know why they talk about sitting on cloud 9? You ever heard that phrase? Where'd that come from? Well, some clown made a list of every kind of cloud there was based on his observation, and number 9 was the big puffy one. So cloud number 9 was the one you wanted to be on if you wanted to just lounge. You know, soft and, yeah, I'm on cloud 9. Yeah, that's beautiful. So, you know, we get a lot of stuff from old things like that. It's kind of interesting to think about the history that came. But nonetheless, what is the difference between these different colors? When we talk about light, what do we typically talk about?
Frequency?
We don't usually talk about it in terms of frequency.
No.
We talk about it in terms of wavelength. Wavelength is the physical size of the wave in, usually in meters. And we give that symbol lambda for wavelength. It's just a different way of measuring a waveform. So wavelength and frequency are related to each other. How are they related to each other? If we wanted to calculate wavelength, how would we do it? I guess that's a quick telephone question. How do you calculate wavelength? I haven't looked it up. Let's see. It's definitely related to frequency.
Wave speed divided by frequency gives you the wavelength.
So the speed divided by what?
Frequency.
Speed? What's speed?
Velocity,
Okay, so normally we use the speed as the speed of light. Which is 300 times 10 to the 6, or 300 million meters per second. We looked at that. Did we look at that the other day, at how slow light really is?
Yes.
But, you know, in our world, on the Earth, it's pretty darn fast. So that's what we use. So basically, in order to calculate the wavelength, we simply take the speed of light and divide it by the frequency. As the frequency goes up, the wavelength gets shorter. I believe the frequency of red light and what happens when we get past red light. And what happens when we get past blue light. what happens then?
Infrared.
Infrared.
And over here? Ultraviolet. All right. What is the frequency of a 670 nanometer wave? So the wavelength is 670 nanometers. What's the frequency of that going to be? That's my little idiot calculator-free math. I have no idea if it's right or not, so maybe somebody else can come up with the actual answer. But 300 times 10 to the 6 divided by 670 times 10 to the minus 9 to simply subtract the two exponents, so 6 minus -9 gives me 15, and divide the 300 by 670. It's just a little bit less than half. 300 over 600 would be half. So if this is a little bit larger, the fraction's going to be a little smaller, so I just guesstimated it about 0.45 times 10 to the 15th. So what'd you get?
I got 0.447, so.
Yeah, close enough.
0.45.
So clearly these things have frequencies that are very, very high. All right, well, this kind of transcends the whole, this is the next step after terahertz, which is the 12th, right? Gigahertz is 10 to the 9th, terahertz is 10 to the 12th, and I don't know what the next one, I'm sure there's a descriptor, a number, a prefix for it, but we generally don't work with it in terms of that, and you can kind of see why. It's a lot easier to work with wavelengths. Okay, so 670 nanometers, I believe, sits squarely in the red zone somewhere. Why is the light that we use in most fiber optics red? Any ideas?
What was it? I'm sorry, what was it?
Why do we use red light?
Is it a shorter,
Frequency less, is it?
What's that?
The frequency's smaller than slower? Easier to bend?
Because different wavelengths travel through different materials differently. And we know this to be true. If you've ever driven down the freeway and heard somebody's car stereo in the car next to yours, what part do you hear? You normally hear the lower frequencies, right? High frequencies are more reflected, low frequencies are more refracted, it seems, at least in the nature of what we do and our hearing and what we experience. So we experience that different wavelengths travel through different materials differently. And it's the same with light. Light travels through different materials differently. That being said, we need to consider the option of FDM. Let's see who remembers what FDM is. What is it?
Frequency division multiplexing.
Frequency division. You get an A for that. Multiplexing. I'm going to make that X a little better. Frequency division multiplexing. What is that? Remember what it was? Bonus points if you can tell me what it means.
Can't remember honestly. Remember
What's that?
messages through different frequencies reaching.
Yeah, you're on the right track. Anybody want to add to that?
Is that when you modulate different, using different frequencies to send a message and then filter it out on the receiving end?
You're on the right track. Very close. Frequency division multiplexing is simply the way we manage radio stations. You have a station at a certain frequency, you tune that frequency, you hear that information. Right? So if your carrier is 100.7 megahertz, then you tune your radio to that frequency and then decode the information that comes in at that frequency. Right? Is there any reason that we can't do the same thing here? Could I send like 620 nanometers and send 680 nanometers in the same tube?
Filter it out.
And then just split the data over here. And over here you've got a filter that does 620. And over here you've got a filter that does whatever we said, 680. So conceptually, does that make sense? Looks like a pair of pants. Does that make sense conceptually? I mean, obviously it works with your radio in your car or wherever. So is it reasonable to extrapolate, since we can convert wavelength to frequency using a constant? Can we then assume that this works for wavelengths as well as frequencies, since frequencies and wavelengths are somewhat interchangeable? Why not? All right. Any questions? Nobody? Did I do a good job then? Nobody has any questions, or are you just so bewildered you don't know what to ask?
Second.
You sure?
How would they filter out the different frequencies with the light? Or is it just the different densities of the material, the cable, or?
Filter out light every time. Remember we talked about what color is the apple?
Mm-hmm.
And we talked about the fact that the apple absorbs every color but red, so the apple really isn't red at all. It just appears red because that's what it's rejecting, right? So you can use different materials to filter out different lights, just like they do at a show. Why do you think when you have a white light and you shine it through a piece of gel at a concert, it comes out red or blue or green? Because you're filtering out, you're only allowing that wavelength of light to go through that filter,
Oh,
right?
yeah.
Or a range of wavelengths to go through that filter. So same thing for multicolor LEDs. You're adding red, green, and blue together and different proportions, and they vary. Red, green, and blue are like red, green, and blue. They're away somewhat from each other, although green and blue are close. But red is way down the other end. So really, you kind of have a really red and blue, right? Red and blue. And they play together real interesting because you got me started now. And red and blue play really interesting together because, and this is something else to consider, in your thought process, is that when objects move away, they turn red. And when objects move towards, they turn blue.
Is that the whole theory behind like 3D movies and the glasses and you got red and blue filter?
No,
No?
that's different. This is more along the lines of interstellar travel and
Okay.
things like that. If you look at the stars in the sky, they're turning red. They're red. They have a red component because they're moving away, supposedly, or whatever, the Big Bang. So they're moving away from you. Just like when you hear a train and it comes towards you, what happens? The frequency gets higher, right? So blue, higher frequency. When the train moves away from you, what happens to the sound? It goes ding, 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 right? It gets lower in pitch. It's moving away from you, the frequency goes down. So the color of light shifts depending on whether you're moving or not. So really, brake lights are kind of backwards. Right? So, there's this aspect, but from this, we've learned that red light has a lower frequency and that blue light has a higher frequency. All right. Any questions other than that? I think I gave you too much for that question you asked me, but hopefully I answered it. Who else? Anybody else have a question I can answer before we put this to bed for the week? Yoslin, you doing all right there? Do. Mr. Skelton, what about you? You're usually good for a few questions a day. Got any?
Nope.
No? Mr. P?
Good. Answered my question.
Nothing? Nothing.
No question had.
Okay, then we are done for the day and for the week.
Right.
We're gonna do this again when? Tuesday? Are we doing Tuesday and Thursday?
Once you-
Does that kinda work?
On Thursday.
Tuesday?
Tuesday and Thursday for going through this until we're done. When we're done, then you don't have to come to class anymore. So we'll get it done a couple weeks, 3 weeks.
It's kind of sad.
Huh?
Isn't that sad?
Why is it sad?
We're coming near the end of you guys.
Yeah, you guys are coming to the end. But it wasn't that long ago that I can recall that some of you guys weren't sure you wanted to come in my class. So, yeah. I'm gonna turn this off.